Hello, we are going to present the proposal of our project. It is titled Development of a Device for Early Plague Detection and Plant Health Monitoring in Ecuadorian Banana Plantation. Banana production is one of the most important agricultural activities in Ecuador because it represents 2% of the overall GDP and nearly 35% of agricultural GDP, as mentioned by Ministry of Production. One third of the global banana export come from Ecuador, and the sector employs over 2.5 million people. One of the main issues affecting banana plantation in Ecuador is the presence of pests in strategic regions of the plant. Early detection of insects becomes very challenging due to their deep location and lack of technology. Especially a pest known as cosmopolites sordidus has been particularly harmful to the banana industry in recent years. This insect causes the death of existing roots, reducing the plant's ability to absorb nutrients. Currently, in Ecuador, various invasive practices are used to detect this pest. However, in most cases, the infection cannot be identified until harvest, when the product is already ruined. Furthermore, the lack of agricultural technology has also obstructed the efficient monitoring of banana plant development. These crops require a substantial amount of water. However, determining the appropriate water consumption for each banana plant has become a recurring issue. According to Ping Lu, measuring sap flow is a precise method that allows to determine the plant's water consumption. Likewise, sap flow is a crucial parameter for evaluating the crop's transpiration level, which in turn provides an approximation of its health and growth. If the sap flow level falls below a certain threshold, it indicates that the plant is experiencing a water deficiency, which can affect its fruits. Now, my colleague going to explain the base design of our proposal device.
In order to address this critical issue, we propose to create an ASIC microchip with the ability to safely detect the presence of the plague while also providing monitoring of the subflow levels in the banana tree. The plague detection will be carried through a bioacoustic sensor attached to the plant's corm, where the insects are most concentrated. Then, the ASIC will be in charge of converting the signal into a digital form, filtering the environmental noise, and detecting the presence of the specific frequencies produced by the weevil, which fluctuate between 1.2 and 2.4 kilohertz. On the other hand, the subflow measurements are obtained using the Granier method, which consists of two T-type thermocouples connected to the plant's core. One thermocouple is heated at time spans, and the subflow density is calculated by using an expression that depends on the temperature and on the temperature difference between the probes. The next diagram illustrates the first schematic of the circuit. It basically consists of analog to digital converters to analyze the environmental signals, filters to eliminate noise, and the controller. This component, which will be the heart of the IC and whose schematic can be seen on my screen, is in charge of detecting the specific frequencies produced by the weevils and also calculating the subflow density of the plant at that moment. At the same time, the IC will be designed to be activated only at the specific times in order to save as much energy as possible. Every plant will need to have their own sensors, but the idea is to design the chip for it to be able to recollect and process the information from a large quantity of trees. Finally, all acquired data will have to be transmitted to a central station, so the IC will be designed with an interface to achieve wireless communication. We began working on the IC during the previous month of September and already developed the initial components of the ADC. It was decided to start the circuit design with one of the most basic components, the operational amplifier. In order to accomplish this, the design chosen for implementation was the operational transconductance amplifier proposed by the members of the Institute of Micro and Nanoelectronics at the University of San Francisco de Quito in 2023. As can be seen below, the proposed design consists of a total of 12 transistors. However, it was decided to simplify the design by omitting the output buffer stage. Similarly, the dimensions of the transistors were recalculated to obtain optimal results. Two different software tools were used for the simulation of the schematic design. The first being custom compiler tool from Synopsys, and the second being the open source program Xkim. The latter was used for the UniCASS design contest during the months of September, October, and November of 2023, as it contains the Sky 130 nanometers libraries. Simulations in both design environments allowed verifying the correct operation of the circuit. Subsequently, the layout stage was continued using the open source software Magic. The result can be observed below. Both NMOS and PMOS transistors have their own respective rings and number of fingers. Therefore, by performing the LBS tests, the correct operation and design of the OTA could be verified, both at the schematic and layout levels. Next, my colleagues are going to explain the design process of the next two components.
Hi, returning to the Xkim platform, I'm going to show two fundamental blocks using our ADC. The first circuit is a MOS-based sample and hold. We look for a variety of topologies, but choose the current topology because of its differential configuration. To ensure that the dimensions chosen are appropriate for the circuit to perform as we expect, we create a test bench that will sample a sine wave using a sample time determined by a clock signal. We can see from the simulation results that the circuit is, in fact, sampling our input signal when the clock signal is in a high state. And when the clock signal starts to go low, the output signal maintains the last sample value. The following circuit is a 4-to-2 CMOS encoder, as we show you. Again, to make sure the circuit behaves the way we need it to, we will run a simulation that will show its performance. As we can see, the encoder provides a 2-bit binary output for the 4 possibilities at the input. Through rigorous simulation, we verify the functionality of the sample and hold and encoder circuits to ensure their reliability by evaluating its performance under various conditions. We determine its effectiveness in maintaining accuracy and consistency, aspects crucial to the overall success of the ADC implementation.
Our layout design process involved two main steps: transistor sizing and connection layout. In this transistor sizing phase, we utilize the Magic platform, an industry standard tool to precisely determine the width of each transistor. This platform provided us with the necessary dimensions to meet our specifications, ensuring optimal performance and efficiency within the circuit. Moving on to the connection layout phase, we translated the schematic diagram into physical connections on the layout. This involved carefully arranging the transistors and other components to ensure the functionality and connectivity of the design. To avoid any potential issues, it was necessary to determine the width of every layer used in the platform for the connections. Following the layout design, we connected a comparison between the schematic and layout designs to validate accuracy and integrity. This involved checking every connection and component placement to ensure consistency and adherence to the original design specifications. Additionally, we performed tasks on capacitances and parasitic resistance in the sample and hold circuit to identify and mitigate any potential sources of error or performance degradation. Despite the complexities involved, our layout design process was ultimately successful in achieving our design goals for the encoder and the sample and hold circuit. By exploiting advanced tools and methodologies, we were able to deliver a layout design that met the requirements of our project.
Thank you for your attention. We hope you find our proposal interesting.